This one, you actually have done this before. You did this in like 5th grade. Like, you just didn't know it was called fundamental counting principle in 5th grade. In 5th grade, they actually probably made you draw little tree diagrams, made you draw these little trees to be like, if you're bringing a lunch and you have 5 choices of what to put on your sandwich and 3 types of cheese and 2 different pieces of fruit, draw all the possible combinations.
I very vividly remember the one where it was like the closing twist.
Yes, you have 5 pairs of pants you can wear, 4 shirts, and you draw this little tree. But some of the smarter kids probably realize, oh wait, I don't have to draw these trees. If I just multiply all of them, I get the answer that I would get from drawing all my trees. Was that any of y'all? Now, if that was y'all, then that was fundamental counting principle. You don't have to draw the trees. Okay, looking at our first one, it says, if a student has 5 different t-shirts, 3 different pairs of cargo shorts, spoiler alert, cargo shorts are not cool, and 2 different pairs of flip-flops, how many different outfits can the student wear? So yes, you could draw a little tree and you could have 5 branches and then 3 branches off of each of those 5 branches and then 2 branches off of each of those 3 branches, and then you could count them up at the very end. Or you could just say 5 times 3 times 2
it's 17.
is 30 outfits. Okay. So again, this is called fundamental counting principle. It's just, I guess it's fundamental. It's the most basic way of counting. All right, we got a small refrigerator for our college dorm. It's got several options of what we can buy. We're buying it from, obviously, Fridge Depot. You can have a regular freezer, a self-defrosting freezer, or no freezer at all. It can be 4.5 cubic feet or 6 cubic feet. And it can come in one of 5 different colors: white, beige, brown, black, or brushed steel. How many different styles of fridge are there? So, starting with, what are my freezer options? How many freezer options do I have? I have 3 freezer options, yes. One of them technically being no freezer. And then size options. 2 size options, good.
And then the color option.
And then color options, 5 color options. I don't know why this came out to be the same numbers as the last time. It's not always going to be like that. So my different possibilities of fridges would be 3 times 2 times 5, which again is 30 options for my fridge.
How would you have a white no freezer? Yeah, how would you have a white no freezer? Or a beige no freezer?
No, that's the option.
There's nothing wrong with having that option. Some people might want that option. Maybe your whole dorm room is white and you just want to match the aesthetic.
Man, how is the freezer option?
You don't need a freezer in a college dorm.
What's wrong with getting a white fridge?
Yeah, exactly. That's normal.
I feel like white is like the default.
Okay, now we're getting into some a little bit more complicated ones that we want to think out. We listening? We listening? All right, Texas state driver's license plate consists of, this is actually old, consists of 3 digits, which you can use the numbers 0 through 9. And there's a space for the state seal, which I think is the shape of Texas. And then 3 letters. The letters O is not used because it's hard to distinguish between an O and a 0. How many different license plates can Texas issue? So a lot of times on these I like to draw out the possibilities. So they said at the beginning we have 3 digits, which just refers to numbers. We can put any numbers here. And then in the middle there's our state seal. So I'm going to draw out the state of Texas. There it is, looking gorgeous. Okay, and then there's 3 letters. 1, 2, 3. And they said, again, the letter O is not used because then it might look like a 0. Okay, so thinking up here, these are all numbers. All of these can be numbers. And it says I can use the numbers 0 through 9. So I have to think in each of those spots, how many possible numbers could go in each spot? 0 through 9 would be 10 numbers. Yes, so I can put 10 different numbers here. I'm allowed to repeat them. It doesn't say anything about, oh, you can't repeat numbers. Yes, you can repeat them. So I can put 10 different numbers here, or I can put 10 different numbers here. Okay, in the back, these they said were letters, but not O.
25.
Very good. Y'all are the first group I've ever had that actually knew how many letters were in the alphabet. Everyone else is like, hey, bank, yes, I remember this previous years. Okay, so there's 26 letters, but if you take out O, that means there's 25 letters. And again, we're allowed to repeat. So we can put all these. And guess what we're going to do with all these numbers? We're going to multiply them. 10 times 10 times 10 times Texas. No, we don't multiply by Texas. Times 25 times 25 times 25. That's why we grabbed calculators for today.
625 times 25.
No, not 625.
15,625,000.
Good. Thank y'all for grabbing calculators. 15,625,000 different license plates.
That's a lot, but like also not very much because
Yeah, there's actually 7 digits on a license plate now. Again, like I said, this is old.
there's way more people.
Right, this would not be enough to put plates on all the cars in Texas.
You can do the like
Was y'all's Texas as good as my Texas? Yours was better? I bet. It doesn't take a whole lot to be better. Okay, we got another one that we kind of have to think out. There's 8 horses in a race. How many different orders can they finish in? Okay, so let's think about this. Here's first place. How many different horses can come in first place? 8 different horses could be first place. Only one of them will obviously win, but there's 8 possibilities for how many can get first place. Now in second place, 1 horse already won. So how many horses can finish in second place? 7.
I specifically like very vividly remember this problem.
Oh, really?
Like this specific one, both of these questions, and me and my geometry teacher. For some reason, my geometry teacher just had no idea how to answer the second one. Like,
That's weird.
I don't know why.
Okay. In third place, how many horses could finish third now? 6. And then we just keep on going. All the way down to the sad little horse that finishes in last place. And then guess what we do with all these numbers? We multiply them.
So what is it going to be? 8 times 8 times 7 times 6 times
8 times, 7 times, 6 times, 5 times, 4 times, 3 times, 2 times 1. Charles, what is it? Yes.
Yeah, that's what I'm saying.
40,320 ways for those horses to place. And I heard quite a few people saying they remember what the notation for this is.
8!
Yes, it's 8 factorial, which looks like, as Danny said, 8, because it looks like an exclamation point. But you read it as 8 factorial. So when I see 8 factorial, that just tells me I need to do 8 times 7 times 6 times 5, 8 times all the numbers below it. Okay. How many different ways are there for 3 of the 8 horses to finish first, second, and third? Well, we just need first, second, and third. We don't need all the places. So how many possible horses could come in first? 8. How many could come in second? 7. And how many could come in third? 6. So this one's... Okay, this question right here, where we had a smaller group of 3 horses picked from a larger group of 8 horses, this is what's called a permutation, when you have a small group picked from a large group. Okay, so this is technically a permutation. There is a formula that you can use for permutations. I don't like using the formula. I like just writing it like this. It's literally the same thing, but easier. Formula is on the back, though. Let's look at it. Oh, hold on. I forgot to cloud my 336 ways. Okay. All right. Permutations refers to a smaller amount of R objects taken from a larger group of N objects. Let's find, where's my green highlighter? There it is. Okay. So we have a small group of R objects taken from a larger group of N objects. Now there is a formula for it. Okay. There's also 3 different ways that you can notate it. I'm going to show you. All 3 of these mean the same thing. These 3 right here all mean we have a big group of N and a smaller group of R that we're picking. This first notation is the one I use in Algebra 2. I'm pretty sure this second one is the one that's used in statistics. And then the third one, I don't know, I've seen it a bunch of different ways. But they all mean the same thing. They all have that capital P, so you know it's a permutation. N is going to be the larger number. This one is the larger number. R is the smaller number that you're picking out of the larger group. Okay, and then let's look at that formula. On the top, we'll have our larger number factorial. On the bottom, we'll have our larger minus smaller number factorial. Now, all of these are possible to do without the formula, because technically we did one on the front. Did we use the formula? No, we definitely did not use that formula. Formula makes it more complicated, I think. Okay, let's read this one. There's 12 students on the student council. They have failed to elect officers because everyone voted for themselves. So the sponsor decided to select the officers. The student council constitution calls for a president, a vice president, a secretary, and a treasurer. That's 4 places, so we need to pick 4 people from our group of 12.
It's all coming back to me.
Good.
I'm remembering why I hated this so much.
What? It's easy.
Yeah, but it's just so it's easy a little like now, but it's so
12 people, and we need to pick 4 of them. So in permutation notation, it would be 12, capital P, 4. 12, pick 4. Okay. And again, we can use our formula. We can also just write out our places. We can write out president, vice president, secretary, treasurer. How many people could be running for how many people could we pick for president? 12. And then for vice president, we already used a person, so 11. And then secretary will have 10 people left. Treasurer will have 9. And then if we multiply all those, we get...
A really big number.
Well, you have a calculator on your desk, Honor. 11,880. They call those slates, which are like the different selections. Oh, I wrote slots. Slates. Okay, I'm going to show you that the formula does work, though. I'm going to do this over on the side just to kind of be like, this is how it works, why it works. Okay, so our formula is n factorial over n minus r factorial. Okay. Out of these two, which is n and which is r? N is 12, P is 4 is the r. So on the top we would have 12 factorial. On the bottom we would have 12 minus 4 factorial. Okay. So if we expand both of these, okay, 12 factorial would be 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And the bottom would be 8 factorial. Which, if you look, that causes any common factor you have on the top and bottom, you could cancel. So what are we left with? The same as what we already calculated. 12 times 11 times 10 times 9 is what we were left with, which again was 11,880. Okay. Permutations with repetition, not reputation. Okay, let's look at what this says. So how many different permutations of the letters Carnegie are there? Just how many different ways are there to arrange the letters in Carnegie? So, obviously, if you wanted to arrange the letters, in the first spot you could put, how many are there total?
7.
4, 5, 6, 7, 8. There's 8 letters.
8.
There's 8 in the first spot. How many would be in the second spot?
8, 9.
7. How many would be in the third spot? 6. So how are we going to write that? A factorial, right. Which would be 40,320 different ways to arrange. Okay. How many of them are distinguishable? Okay, so distinguishable, nice try. Distinguishable means some of these actually repeat. Why would some of these be repeats? Yes, because we got a double E in there. So this 40,320 doesn't separate the two E's. It calls those the same. It looks like those are the same thing. So we have to divide out those little repeats. So we would take our 8 factorial and we would divide by the number that repeated factorial. So that would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 2 times 1. So we really just need to do 8 times 7 times 6 times 5 times 4 times 3. Was that hard? Was that hard? No. I think there is somewhere, but honestly, I don't think it's any easier than just typing them in. Look at, like, basically halved them. It did halve them, yeah. Mm-hmm. Yes, because of those repeats. Okay. The number of distinguishable permutations of n objects, where one object occurs S1 times, and it's possible that 2 letters repeat. Another object occurs S2 times. It's possible that 3 letters repeat. Every time you have to divide out those repeating letters, and you don't want to combine them. So like say you have like 3 A's and 2 E's, you don't want to divide by 5 factorial. You want to divide by 3 factorial, 2 factorial, or whatever. Let's try it on some of these. So I'm going to start by counting the total letters. 1, 2, 3, 4, 5, 6, 7 total. So we'll have 7 factorial on the top. And on the bottom, we're going to divide by any repeat factorials. Which letters repeat? The O, right. So we'll divide by 2 factorial. Those 2 times 1s are going to cancel, and we just need to do 7 times 6 times 5 times 4 times 3, which is 2,520. All right, looking at the next one. We get how many total letters? 9 total, so that's going to go on our numerator. What do you see that repeats? How many E's? Oh, we got 4 E's. And then, what other letter? R. There's got 2 of those. Remember, you don't want to combine them when you want them. You want to write them as separate factorials. So we'll have our 4 factorial for our E's. And we'll have our 2 factorial for our R's. Now, does this become 6 factorial? No. We want to write them out separate. On the bottom, let's see, we got 2 things. We got a 4 factorial, which would be 4 times 3 times 2 times 1. And we got a 2 times 1. You can actually simplify this before you do it in your calculator. Like, I look basically on the top and bottom and I say, does 2 divide into anything, any of those numbers on the top? Yeah, 2 divides into 8. So I'll cross out that 2, cross out that 8 and write a 4. So I really just need to do 9 times 7 times 4 times 6 times 5, which is 7,560 different ways to arrange those letters, but they're all distinguishable.
Why did you put 9,
Yeah.
7, 8, 6, 5?
9, 7. I don't know. But it worked. I at least got all of them. Sometimes I do this so quick, sometimes I forget a number. Like I'll forget a random 5. Okay. Mississippi. How many total letters we got in Mississippi? 11. So we'll have 11 factorial on the top. On the bottom, we got 2 S's. What else we got? Oh, 2 P's. 4 I's. Yeah, 4 I's. 1, 2, 3, 4. Alright, so we'll have a 4 factorial for our S. We'll have a 4 factorial for our I. And we'll have a 2 factorial for the P. Okay. 11 times 10 times 9 times 8 times 6 times 5 times 4 times 3 times 2 times 1. Let's see. One of the 4 factorials will cancel with this 4 factorial. And then I'm going to have another 4 factorial. And then I'll have a 2 factorial. Alright, let's see what we can cross out. Obviously, one of the 4 factorials cancels with the end of the first 4 factorial. The others, we can do a little bit of simplifying before we try and... Oh, I missed a dot. Okay. The 4 can go into what number on top? The 8. So I'll get a 2 there. The 3 can go into what number on top? A 9. Okay, and then what else do I have left? I have a 2 and a 2. Yeah. 2, make that a 5. 2, make that a 3. It really doesn't matter which one you simplify with. So left over I got 11 times 5 times 3 times 2 times 7 times 3 times 5. On the bottom I just have a bunch of 1s. Let's see. 11 times 5 times 3 times 2 times 7 times 3 times 5. 34, 650. Is that what you got, Rashida? Good. 34,650. Okay.